All right, so we just went through a little warm-up problem, just mainly one in units conversion, taking a word problem, so to speak, and turning it into a engineering problem. Now, let's go back to the shell. I think today we'll be able to hit on some of our problem set work. We're also going to hit on the summary here, and then in the final third of the course, we'll take a look at the chapter. Oh, let's take it. Well, first of all, here's the paper, and I also want to go through and describe part of my motivation for writing this paper in the first place, in case I hadn't talked about this much before. A big part of my motivation for writing this was trying to understand our fascination with fossil fuels, and why the United States, felt or feels compelled to defend a lot of the oil wells around the country. And from my very naive perspective at the time, as you can see, I wrote this several years ago. I was on the faculty at Drexel University at the time. I first started thinking about this almost a decade ago, and wondering, why, we're putting troops in harm's way in a very volatile region of the world just to go after oil. I'd been building solar cars and looking at renewable energy, and it wasn't until I looked at this quantitatively that I really started to understand it. I started to figure out that 10 million to 1 ratio that we worked out the very first day of class, and I'm like, gosh, petroleum products are extraordinarily energy dense, way more than the renewables. And why is that? Well, the Earth has been collecting energy in the form of sunlight and converting them into fossil fuels for the last however many billion years or 100 million years that you want to discuss. So when it comes down to it, and I think now we have a pretty good handle on what joules are. We know that there's 10 megajoules in one human energy, and I think Joe and I, we went through kind of like, gosh, what is a gigajoule? What is an exajoule? And each time you stick an extra prefix on there, you're going up by a factor of 1,000. So we went through a little exercise going from a cubic centimeter up to a liter, up to a cubic meter, up to sort of volumes the size of the city of Missoula. And so it's not that easy to just sort of think about what a gigajoule is, but knowing that one human daily metabolism is 10 megajoules. We know that 4 people would need 40 megajoules, and then looking at this guy, 45 gigajoules, that's 4,000 people. So we can right away hop from a megajoule up to a gigajoule, and there you are at 4,000. So that hopefully that kind of puts those types of numbers in perspective. And you come way down here, solar energy density, 5 microjoules per cubic meter.
Well, really, so you could run 4,000 human beings basically on a cubic meter of oil.
Yes, 4,000. If humans could metabolize oil, if we had the enzymes in our bodies to break that back down into a hydrocarbon form, 4,000 people could slurp on that cubic meter of oil in a day and be just fine. So yeah, and it's not unlike packing that many cheeseburgers in a cubic meter either. I mean, there's oils that we can digest in a cheeseburger, and somewhere down further in the paper I talk about the energy density of fuel. But you can imagine, jamming a few thousand cheeseburgers into a cubic meter and feeding the masses with that. So the analogy holds, but it's just that our technologies consume the hydrocarbons, the long chain fossil fuel hydrocarbons. So getting back down to this guy, 1.5 microjoules per cubic meter. Now when I first wrote this paper, I got a lot of pushback and you guys are going through this now with your own uploading your summary one. You're doing your own peer reviews as you put your papers up, and you're kind of exposing yourself to the world for criticism. But frankly, that's exactly how science moves forward. If science were not true and did not hold the test of time, it goes away. It goes away as myth. So that's part of the peer review. And I really had a hard time convincing the reviewers that, yeah, in a 1 meter box of space, so just, think of a 1 meter box of space that's about the size of half your fridge. There are photons in there. There is light inside that. Obviously, they're sort of passing through that volume very, very quickly. But if you summed up all those photons, energies, it's 1.5 microjoules. So 1.5 thousandths of a joule. So then now the big numbers really come out. Oil is 20 quadrillion times less energy dense than oil. And that's why you kind of got to wait around a long time to charge your battery with your little solar panel. So that was kind of the big picture. I was also hoping that this paper would reach a wider audience. I kind of hoped that I would just publish it in like Cosmo or Women's Journal or something. It would be sort of be sitting there next to the Inquirer as you checked out the grocery store. Like, oh, I get it now. But I don't think it worked out because I use big words. Yeah, words are like quadrillion. But and I tried. I mean, I really did try to. And we just did a little bit of kinesthetic learning a second ago with me running around and throwing books and all that kind of stuff. But if you scroll down here, I tried to make a graphic comparing some of these big numbers. Well, here's one graphic just showing if I'm going to idle an automobile, I'm going to need about 15 human powers just kind of pedaling to keep the chains and the belts and the pistons moving up and down. And so you can imagine as the car is sitting there, sort of going 0 miles per hour. It's running, and we just did this calculation a second ago, it's probably running about 1 horsepower, maybe 3 horsepower, and that's about 15 or so human powers, right? So there's a little visual for you. And the same thing, if you're running at, 10 times that rate, and again, I've got it right on this figure, just like we were talking about a second ago. There's your miles per hour, and there's your watts. Those are both rates. One is the rate at which energy is being consumed. The other one is the rate at which distance is being covered. You're going to need 150 people pedaling their hearts out to push that poor car through the road at 50. So that's why we don't see human-powered buses running up and down I-90. Just fundamental physics. And I've had students come up and say, "Oh, we should make human-powered cars." I'm like, "Well, we got them. They're called bicycles. It's already been invented."
The same Fred Flintstone was a badass.
Fred Flintstone was a badass. There you go.
Visionary.
Yeah. And okay, see you right. And then so the next bit, I was trying to do something true, just trying to give a graphical illustration of what 1 millionth is. I think I covered this briefly in a previous lecture, but the tiny blue dot, and this is the blue dot here, is 1/10,000th of this circle. So there's 10,000 little of these guys inside, and the square root of 10,000 is 100. So you can think of like 100 by 100 if this thing were a square. And then the black circle is 1/100th. So 100 times 10,000 is 1 million. So, and you can't even really see the dot there, and that's a millionth. And I just told you that the sunlight is a quadrillionth. So, that's 10 to the 15th times. So anyway, the numbers are big, and sorry if they're confusing, but unfortunately, that's the world we live in. That's part of the sport, and I don't know how else to describe it any better. Okay. So hopefully, and sometimes people talk true costs, and one thing I was looking at in terms of in terms of investment, I did another little calculation. I don't think it's in this paper, but I looked at the dollar value of the amount of oil that is underground in Iraq, and it turns out it's about 10% of the world's remaining petroleum reserves. And when you run that out in terms of $50 a barrel or $100 a barrel, the numbers add up pretty quickly. And it turns out there's about 7 or 8 times as many dollars worth of oil underground in Iraq than it costs us to maintain that military campaign. So from a purely economic standpoint, it was a worthy investment. So from a political standpoint, I'd say, well, gosh, that really caused George Bush a lot of flack, and it might have marred the the American image overseas. Why are these guys running around worrying about oil fields so much? But from a purely economic standpoint, you can look at it as a very good investment. So, and of course, in any decision, you have multiple variables that you're considering. So, okay, well, that's kind of the big picture on this paper. And any questions at all while we're kind of just taking a look at it here?
The truck versus the low mileage truck versus the high mileage car.
Yeah.
Problem.
That's
Could
a
you
tough.
explain that a little
That's a good one, isn't it? Yeah. Let's look at it. Let's see. Let me see if I can just find it here. This one?
Scroll up a little. Yeah. Yep.
Oh, yeah, that's a good one. Oh, yeah. Okay, let me just read through it and refresh my memory. In the August-September 2007 issue, James Click encourages truck owners to consider the responsibility of American citizens to become less energy dependent by purchasing vehicles that get better gas mileage, right? And so, and there's a big discussion about energy security, and now we're very proud of the fact that we're a net exporter, and we talked about that a little bit. So you can sort of look at that as a security issue. And so in terms of making our own energy go farther and making us more energy independent, the logical conclusion would be to make the energy at home, and you're gonna use it here. And well, if you're gonna drive, why not do it in a more efficient manner? So that's kind of the first premise. He states that a truck owner who decides to purchase a vehicle with 14 miles per gallon rather than 16 miles per gallon will save as much fuel as a car owner who drives a car with 51 miles per gallon rather than 35 miles per gallon. Okay. A reader from Denver, Colorado responded stating that Mr. Cush must have dozed off in math class because according to his calculation, the car owner would save 8 times more fuel than the truck owner. Okay, so hopefully this makes sense. There's no secret here. What we're looking at is the fact that the difference in the miles per gallon is 8 times. So this is so 51 miles per gallon in a super high efficiency car versus 35 miles per gallon in a moderate fuel efficient car. The difference in miles per gallon is 8. So going, for driving, let's just drive for 1 mile. Well, let's see, miles per gallon. No, let's just give you 1 gallon of fuel. Let's start it that way. We'll give you 1 gallon of fuel. This car right here is going to go 51 miles. This car is going to go 35, and I'll draw this up graphically in a second. This truck would go 16, and this truck would go 14, or 2 miles more. Now, so the mileage difference is in fact 8 times. But it says, indeed, the reader was wrong and should have been paying more attention in his math class. What the Denver reader did not do was to calculate the annual fuel consumption for both vehicles individually. So, and now all I'm doing here, this is 51 miles per gallon. And let me write the units out. I think that'll make it'll make more sense that way. So I'll just write this guy out.
Is that how many miles you're saying?
Yeah, let's do it that way. So let's see if I can get both these things on the screen at the same time. Okay, so basically what we're looking at is so we're going to have car 51, car 35, truck 16, and truck 14. Now, let's just say I give them each 1 gallon. Try to write backwards here. 1 gallon. That car is going to go 51 miles. Let's just call that 51 miles. This guy is going to go 35. The truck is going to go 16, and the worst fuel efficient one is going to go 14. So that's how far each one of these vehicles will go with 1 gallon of fuel. But that's not how we drive. We go from one destination to another because this guy's going to run out of fuel before he gets to his destination. He's going to actually buy enough fuel to make it all the way, obviously. So what I've done is say that if each of these 4 drivers goes 15,000 miles per year, so now they're all going 15,000, 15,000, 15,000. They're actually all going the same distance. So if this is your 51, this is your 35, this is your 16, this is your 14, the next thing I'm going to draw is not going to be to scale, but what I'm going to try to show is that this guy is going to sort of stretch his gallons out. Here's 51 mile chunks. Each one of these represents a gallon being consumed. Here, this is 35 miles per gallon. Every click mark of my pen, I'm burning a gallon. Here's your 16, etc. So obviously the gallons are pouring through the vehicle more quickly. And you can think of each of these as being a joule or 45 megajoules. That's what or 135 megajoules. That's what a gallon is. And here's your 14. Kind of similar to the 16, but more frequently. So there's how to get a visual on that. Now, going back to the equation, the question is comparing these two versus these two, which one saved more fuel? So we actually are comparing apples and oranges here. The car being the apple and the truck being the orange, or what have you. So the car, the equation. So I'm looking at. Let me see this guy one more time. So let's do the car 51. So let's just car 51. So the gallons for 51 equals miles per gallon times miles. So this is going to be the total number of gallons. So the car going 51 miles at 51 miles per gallon. Okay, one sec. Yeah, I know I'm going to get confused here. Really quick. Yeah, I think, you know what, I did kind of jam that all into one little deal here. Let's turn it around and let's do gallons per mile, and that way we can get at the total number of gallons burned. So let's do it this way. It's going to be 1 gallon for 51 miles. And if we multiply that by 15,000 miles, what's that come out to? 1,500 divided by 51 equals 249, or sorry, 294. Okay, so the fuel efficient car is going to burn 294 gallons. Now let's go with the less fuel efficient car. So I'm looking at 1 gallon for 35 miles, and we're going to run the thing for 15,000. So 15,000 divided by 35 equals 428. So the difference in the cars equals 428 minus 294 equals minus 294. 134, 135. 135. So that's where that number comes from. This whole thing, it's really hard in a paper like this on one line to get the thing right, but that's exactly where that number comes from. So let's do the next one. So for the truck, so if we're looking at, and I'll just do this a little more quickly, 15,000 divided by 16 equals 15,000 divided by 14 equals 1,500 divided by 16 equals 937. And then we'll do the same thing, 15,000 divided by 14 equals 1,071. 1,071 minus 937. There's your 134. So anyway, and again, this is just an example of people arguing in public over arithmetic, which is just inappropriate. So I don't know how you really justify that, but that's more or less what was happening in this article. And I'm like, well, gosh, guys, just do the math and write the thing out. So there's not a whole, but it is confusing at first glance. It's confusing in the exact same way that power and energy are confusing, because in this first equation we're comparing power to power and rates of consumption to rates of consumption, and so yeah, the difference is 8 times, but if you're actually trying to ask how much fuel you will save, the trucks, the trucks are consuming so much more fuel that a small difference in their total consumption is going to equal the difference in the 2 cars that are consuming a lot less fuel but at much smaller rates. Okay, so yeah.
Well, it's crazy, if you times all those numbers by 3, to say roughly $3 a gallon.
Oh, $3 a gallon, yeah.
Just to say,
sure, yeah.
roughly, the 51 miles spends 882.
Mm-hmm.
Then the 35 is 1,285. Then the 15 is 3,000, and the 14 is 3,214.
Yeah.
So it's a huge difference between the money you spend yearly,
Yeah, I mean,
$3,000 versus 800.
right, I mean, just about, well, if you're driving, again, this is assuming that all vehicles drive the same distance, you can pretty much multiply your, well, yeah, just
Crazy enough to justify invading another country. That's what it boils down to.
yeah.
They're like, woo, every truck, 3,000.
Yeah, adds up to some big dollars, yeah.
Definitely.
Yeah. So, and well, I don't want to get into a political debate about it, but, frequently, almost invariably, conflicts are started over an actual shortage or a perceived shortage, and whether that's of resources or of money or of what have you, that's where it comes from. Okay. Well, we got about 10 minutes left. We've done a good quantitative problem with the warm-up Tim gave us. We looked a little bit at the summary. Went through a good quantitative question in the summary, so I'll take a quick break here.
Real quick about what we've seen so far in the summaries and the peer review.
Oh, yeah, let's do that. In fact, yeah, maybe we'll just, let's do that, Tim. What do you want to discuss on that?
The peer review looks really good, and you guys are giving each other good feedback. Make sure you're giving each other feedback both on the information involved in the summary, the body, what are the meat and potatoes of the summary. And you guys are doing a pretty good job of that as far as writing style and what kind of information is involved in there. But at the same time, get into the technical side as well. If you look at it and you're like, okay, Brad drew up on the board the other day what the summary is supposed to look like, what the format is supposed to look like. If they don't have that, you need to catch them on that. Cover both sides of the equation, both the quantity, meat and potatoes, but also the format. Both are equally important to make sure that you can have the best paper in the world, the most well-written, but if it's missing all the format stuff, it's still not going to fly. So make sure you're hitting on both sides of that equation and your feedback.
Yeah.
But for the most part, it looks like you guys are giving really good feedback to each other, and the papers are looking pretty good. So, give them one more run. You should be looking at everybody else's papers, kind of not only giving them feedback, but compare that to what you have. Does that paper look anything like yours? If it doesn't, why is it different? That's kind of the purpose of this, besides you helping out your classmates, is the fact that you also get to see other examples of what they look like.
Yeah, so just to reiterate what Tim said, you're kind of reading the paper on two different levels. One is making sure that all the components are there, and the other one is, as you said, kind of digging into the meat. Are they actually doing a proper analysis of it? So, thanks. And probably the most important one to read, I just saw it here for the first time. That would be Tim's chiming in there. So issues with paper so far so read the Big Fish guys post there. But yeah, I mean what I'm seeing so far is pretty good. And it's not really it's not all. I mean, you're not necessarily here. I mean, sure, it's great to say nice job, but it's also, we're not here to kind of give false praises. I mean, the grading will come down between, when Tim and I read through these, so just don't be afraid to point out the flaws in your classmates' papers either. Yeah, cool. And also, I want to just say this for the record, everybody should be updating their profile picture, because I do see a lot of you guys in Lyme. It's nice to have
If you have a bigger fish picture, feel free to.
Yeah.
I'll Photoshop.
No Photoshop in your fish pictures allowed.
So could you just quickly show me again where you go and add a picture to it?
Oh, yeah. So if you haven't done this yet, I think
There.
it's just my profile,
Okay.
and then edit profile.
Oh, and there. Got it. And then,
User picture.
okay.
There it is.
You're the only person I've ever heard say put your profile picture on there.
I don't want to look at a bunch of schmoes and all. What the heck is that, man?
It's a lot easier when you have 20 or 30 students to be able to put a face with it.
Yeah.
I suppose.
You get to express yourself. Use your